Hello and welcome to the LETP, or Learning and Understanding Electronics Through Simple Projects. This is the first episode of the series and it might very well be the last, depending on if this is successful, if the three of you that actually watch my channel find this interesting. So in today's project, my dad bought a camper, and that in itself isn't a problem. The problem is that he wants to use that camper parked on the construction site where he's working, where there is no electricity or running water. In that camper, he wants coffee, light, radio. So to get around the issue of not having coffee, light and radio, he got a gas cooker, which solves his coffee problem. But although making a gas-powered light and radio would be a neat project idea for a video, that is not our goal. Okay, so the camper has a nice lead acid battery, which would typically get charged by a car engine, but since in our case the cabin will just be parked in the same will be always parked in the same space on the construction site, it will not be connected to a car, and since it's on the construction site, the only source of electricity there would be a big generator, and those are loud and costly to operate. We want to avoid that. So the most logical solution to this problem would be to add a solar panel. This looks oddly like a Minecraft light sensor, but it is a solar panel to charge our battery instead of our car. Now, how do we do that? Now, the simplest solution would be to connect our solar panel like this directly to the battery. Now let's stop for a second and think what would actually happen if we connected a solar panel directly to the lead acid battery. So if there is sun outside, the voltage of a, say we're using a 12 volt solar panel, would rise to around 21 volts open circuit. And since 21 volts is more than our 12 volt lead acid battery, one would think that the solar panel would just charge the lead acid battery and we would all be happy. But wait, there is nothing to limit the current, which means that this circuit would not last all that long before something explodes. Well, that's where you are actually wrong, because there is something in the circuit limiting our current. Now, it sure as hell isn't our lead acid battery, which has a few milliohms of internal series resistance. It won't be our cables, because a good quality copper wire won't drop more than few volts unless it's way too long for its purpose or way too thin. That leaves us to a solar panel. Now, a solar panel is not a perfect power source, which means that it doesn't generate 21 volts and keeps it there no matter what, like say a battery or a power supply would. It actually generates, it isn't, but let's simplify this circuit by just saying that our solar panel doesn't generate constant voltage but constant power, meaning that the more current you draw from this 21 volts, the more the voltage will drop. And since we are connecting the source, we are connecting the solar panel directly to a 12 volt lead acid battery, that means that this voltage must drop to 12 volts, and whatever current is needed for the solar panel to drop from 21 volts down to 12 volts is the current that we will have flowing through the wire and charging our battery. So in theory, this circuit could absolutely work without catching on fire. Well, that's where you are wrong. Because what happens when there is no sun? When there is no sun, that means the solar panel is no longer generating our 21 volts. It is generating closer to like 3 volts. Now we have a lead acid battery whose voltage is way higher than the solar panel, meaning that now instead of solar panel charging our battery, now our battery will dump a whole lot of current into our solar panel, thus destroying it. Now we don't actually want that, so what would be, let's think about it, what would be the simplest solution to stop this from happening? Well, let's add a one-way valve, or in electricity, a diode. Now, this diode will allow the power, this diode will allow power to flow in one way, but not the other. Meaning that if this side is more positive than this side, the diode will let the power flow through. And if this side is more positive than this side, meaning that our solar panel is not generating anything and the lead acid wants to dump the power from it, wants to dump our power to the solar panel, and the diode won't let the current flow from this side to this side, meaning that this is basically all we need to charge our lead acid battery from a solar panel. But wait, there's more. Since this is a lead acid battery, it's as it charges, its voltage will rise from 12 volts to 12.6 volts, and since there is nothing to limit the solar panel from keeping charging it all the way up to previously mentioned 21 volts, well, there is nothing to save our battery from overcharging. Now, since this circuit is fantastically simple, let's utilize this part of the circuit and somehow make sure that the voltage of the battery never goes over 12.6 volts. And how would we do that in the simplest way possible? Well, say this is our solar panel. This is our battery. Here is a negative, and here is the positive. Now, we already said that we need a diode, but why use a standard inefficient diode if we can use a Schottky diode? So that's the first little improvement to our questionable circuit. Now, we need to add some sort of a switch in order to stop the battery from overcharging. Now, let's add a little switch here in a form of a P-channel MOSFET. Yes, I am aware that this is not a this isn't a proper symbol for a MOSFET, but it's just easier to draw it and to demonstrate. So this is a P-channel MOSFET with its 3 wires, and this is a N-channel MOSFET with its 3 wires. Now this P-channel MOSFET will act like a little switch. Now how do we control this little P-channel MOSFET? Now, important thing to know about a P-channel MOSFET is how it really works. This is the gate of the MOSFET, this third pin, and if it is pulled down to the negative wire, the MOSFET will act like a closed switch and let the current flow through. So, and if we do not want the P-channel MOSFET to conduct or act like an open switch, we want to pull this wire up to the positive rail. And how we do that? So the simplest way to drive a P-channel MOSFET like this is, first let's add a simple pull-up resistor to the positive rail, meaning that if there is nothing connected, if there is nothing else pulling this wire down, that our MOSFET will always stay open, with meaning that there will be no current flowing through it. Now, how do we pull this wire? How do we pull this wire to the negative rail? But only when we want to. We'll use a simple NPN transistor, which, if we give it pulse, if we give it voltage to its base pin, it will act like a closed circuit between this wire and this wire, thus pulling the potential on this wire down to minus and closing this P-channel MOSFET. And what did we get? And what do we have now is we basically have a P-channel MOSFET which is open by default, meaning it's not letting the power flow through, and if there is signal given to this transistor right here, if there is voltage given to the base of this transistor right here, that this P-channel MOSFET will turn on and let the power flow from the solar panel to the battery. What will we use to control the base of this transistor right here? Well, first of all, we cannot control the base directly, so we will add a simple current limiting resistor, and then we will add an op-amp. Now, yes, this is an integrated circuit, but fear not, young electrician, it is super simple. So this is an op-amp, plus minus, this is the output and this is the input. If you want to be more precise, you will draw the positive and negative, meaning that it is an integrated circuit, so it needs power. So in our case, our positive and negative are connected, of course, straight to the battery, so the chip gets power from the battery, and then we have two inputs and an output. So when an op-amp is used as a comparator, it's pretty straightforward, I would say. So this is the output and this is the positive input. This is a positive input and this is a negative input. You see, I draw a little plus and a little minus. So in a nutshell, how this chip operates is, as long as the voltage on the positive input is higher than the voltage on the negative input, the output will be pulled high, and if it isn't, the output of the chip will be pulled down low. We need to use this logic I showed here to control our little transistor to stop our battery from exceeding 12.6 volts. So the logical answer after seeing this would be, oh, okay, so if we connect the negative input of the op-amp directly to the plus of the battery, and we give it 12.6 volts on the positive of our comparator, and now we created a very simple logic saying that as long as this wire right here, which is connected straight to the battery, meaning that as long as the voltage on the battery is lower than our 12.6 volts reference, the output of the chip will be high, turning this little MOSFET on. And yeah, in a nutshell, that is all we need. But there is a problem. If our battery is under 12.6 volts, say our battery is at 12.3 volts, where do we get this reference voltage from? That would be quite tricky. So the best thing we could do is use a voltage reference which we can generate from both an empty battery at 10.8 volts and a full battery which is 12.6 volts. So why not use a little linear voltage regulator, which can be, say, 7805, which has 3 wires. It looks like a transistor, but basically the way you use it is you connect the middle wire to ground. First wire goes to basically any voltage between 7 to, I think, maximum is 35 volts, and the output will be always 5 volts. Now let's use that as a reference. Instead of 12 volts here, we'll give it 5 volts. What did we do now? We basically broke the circuit. What we did now is we made a logic that turns off this MOSFET on the battery is over 5 volts, which is a big no-no because a lead acid battery should never reach that low, and we also want our battery to reach 12.6 volts and not only 5 volts. So what we will do is we will not connect the negative input straight to the positive of our battery, and we will use a voltage divider. Since our reference voltage is 5 volts, if the maximum voltage we want the battery to reach is 12.6 volts, that means when the battery is at 12.6 volts, this divider here of 5 volts. Now we created a very simple logic circuitry that says that as long as the voltage on this battery is under 12.6 volts, this MOSFET will be closed. And when the battery reaches 12.6 volts, our MOSFET will open, thus stopping the current flow from the solar panel to the battery. And that's it. We basically designed our own very stupid but functional solar panel charging circuit. Okay, now I want to add a red diode indicator to know when the battery is charging. Now a logical thing would be, because this output right here is high when this MOSFET is turned on, meaning that if we simply add a diode right here, with a simple resistor to ground, we will indicate with this diode every time that this MOSFET is turned on, thus indicating every time when these two wires are when the MOSFET is turned on and letting the power flow from the solar panel to the battery. Well, yes, smartass, but you didn't think of one problem here. What if there is no sun? Now we have a problem, because the solar panel is no longer generating 12 volts, meaning that there is no current flowing from the solar panel to the battery. So what is going on inside of the circuit instead? Well, let's investigate. So the battery, because now it is no longer being charged, its voltage will always drop just a little bit. It might not be a lot unless there is a big load on it, but say there is very little load and our voltage dropped from 12.6 volts down to 12.59 volts. I mean, it's really not much. It's really not much, but it is enough for this voltage to right here to dropping this voltage from 5 volts to just a little tiny bit under 5 volts, but that small amount is still an amount smaller than our reference voltage, which is always at 5 volts, meaning that our little comparator will say, oh, okay, so the voltage on the negative input is smaller than the voltage on the positive input, time to turn on the output, meaning our MOSFET will be activated and shorted from this pin to this pin, and our LED will turn on even though there is no sun on the solar panel, thus meaning that charging isn't happening, because yes, this MOSFET is closed, meaning that it does allow current to flow from this side to this side and also from this side to this side, but there is this little diode right here, meaning that the power from the positive of our battery will go all the way, it will all the way to our MOSFET, pass straight through our closed MOSFET and hit this diode, and it can't go further because this little diode is allowing the voltage, allowing the current to flow only in this direction, meaning that yes, in the dark, in the darkness, when the solar panel isn't generating anything, our MOSFET will always be closed, but it will not do any harm. The issue, however, is that our little indicator LED will constantly be lit, even though the circuit is allowing the current to flow, but it isn't happening. Let's investigate how can we make this LED light up only when the solar panel is actually charging the battery, when there is something on the solar panel and it is actually charging our battery. Now, believe it or not, it's way simpler than it looks like. So charging is only happening when the voltage across the solar panel is at 12 volts, meaning that we can use this pin right here as the positive input to our indicator diode. Meaning that now if we connected this the other side of this diode directly to ground, we would have a diode which is only glowing when the solar panel is generating voltage, meaning that only when the sun is out this LED will be lit up. But we don't want that. We want this LED to glow only when both this channel when both this solar panel is generating voltage and this MOSFET is turned on. Now, how could we do that? The positive side of the diode is connected straight to the panel, and that's okay. Now, what would happen if we were to disconnect this wire right here and connect this diode directly to the gate of our MOSFET? Now let's investigate. Now, before, the negative of this diode was connected straight to the negative, but now it is connected to the negative through this transistor, meaning that the diode can only turn on if this transistor is closed and connecting its negative side straight to ground. And even if this transistor is pulling its the diode's negative wire straight to the ground, and there is no voltage on this pin, the diode still won't turn on, because the voltage difference across the LED is still zero, because this point right here is at 0 volt potential when this transistor is closed, and this side of the diode is also at 0 volt potential because the solar panel is not generating any voltage, and the voltage from the battery cannot get to this point because this little diode is blocking it. Now, what happens when there is voltage on this solar panel? Now we will have 12 volts on this at this point, and we will have 12 volts at this point right here, and we will have 0 volts on this point if this transistor is closed. And let's remind ourselves, when this transistor is closed, that means that this p-channel MOSFET is also closed, allowing the power to flow through. But what if the charging is finished and this MOSFET is open? If this MOSFET is open, that means that this transistor right here is also open. Now we have positive from the solar panel flowing through our diode through this wire. It cannot go to the gate of the MOSFET because the gate is acting essentially like a capacitor, so there is nowhere for the voltage to go. It cannot go down to ground because this transistor right here is open. It can only go through this resistor back to the positive rail. And since both this point and this point of the circuit are positive, well, the diode, there is no voltage drop across the diode, and the diode won't illuminate. And when the voltage of the battery drops because it's not being charged, this transistor will turn on, and the current will flow through the positive, through the resistor, through the diode into our transistor, and the diode will illuminate. There is a mistake in this circuit that I just realized. What did we say our solar panel is generating when there is no load on the output, when there is sun? It is generating around 21 volts. Meaning that if this MOSFET right here stops the current flow from the solar panel to the battery, that means the current is no longer limiting this 21 volts. Is no longer limiting the voltage of our solar panel, meaning that the solar panel voltage is no longer 12 volt. It will rise up to 21 volts. Our battery will remain at 12.6 volts, and the circuit will work just fine. The issue I just noticed is that if there is 21 volts on this point, that means that there will be small amount of current flowing from this point through our resistor, through the diode, through this resistor here, even though this MOSFET is not open. And that is a problem because that means that our LED is going to illuminate when this MOSFET opens, and it will open when the charging is done, and we want the LED to not illuminate when to turn off when the charging is done. So how do we fix that? Well, the simplest way really to fix this problem with this circuit is really just instead of this resistor right here, to put it right here. Now we still have the exact same effect of keeping this MOSFET turned off by default when this transistor is not open, because the voltage on its gate is pulled up instead of down. But now the difference between this point going through the resistor, through the diode, and through the resistor is essentially 0, because there is 21 volts here and 21 volts here. That just means that our LED will no longer illuminate when the charging is finished. And that's pretty much it. That is our entire charging circuit of questionable solar system. Now we just need to add few values. This P-channel MOSFET, you can use any P-channel MOSFET as long as it can handle enough current. This resistor right here, you can use, say, 10 kilo ohms. This Schottky diode, I will most likely just use whatever I find in like a this is a motherboard of a ATX power supply, because it features these quite big and powerful Schottky diodes. This resistor right here, we can use 1 kilo ohms, so we have a nice and bright indicator light. This transistor right here, you can use, if you want to use the transistor, you can also find inside of an ATX power supply. You can use a C945, which is a very common transistor. You can find it in multiple places in these ATX power supplies, or this base driving resistor right here. So this is a C945. This will be a simple red LED. This base driving resistor right here, you can use, say, 1 kilo ohm. this part of the circuit we removed. 5 volts reference will will be using this little 7805 regulator, and for the voltage divider you can use a free online voltage divider calculator, or you can be a lazy freak like me and use a little potentiometer. Now, the only problem with using a potentiometer, this being this pin, this being this pin, and this being this pin, the only problem of using a potentiometer is that you need to later adjust its value. And how do you do that? How I do that, at least, is I I take a fully charged battery. I connect a fully charged battery, which will be at 12.6 volts, and just measure with a multimeter voltage between ground and the slider until I get exactly 5 volts, and that will limit your, and that's how you get this divider right here. And as our op-amp, you can use pretty much any. I like to use an LM358, and that's pretty much it. The entire circuit, I hope, explained as good as I could. This was a part 1 of this video. I'm already recording for 1 hour and 11 minutes, so this is already a lot for a new hobbyist to absorb. So I decided to split this video in 2 pieces. This was a part 1. In a part 2 we will create an overload and a under voltage protection for our battery, so it doesn't discharge way too low, because that would damage our battery. And maybe in part 2 or maybe in part 3 we will assemble the circuit and test it. Any questions, any feedback, positive or negative, is welcome down in the comments, and see you in the next video.